Welcome to Applications of the Equilibrium Constant. So, knowing the equilibrium constant allows us to predict a few things. Whether the reaction will occur, but not the rate of reaction, just whether or not the reaction will occur. Whether the reaction is at equilibrium or not. And it allows us to predict the equilibrium position given the initial concentrations of the reactants and the products. So let's examine some reaction. So here I have displayed graphically a reaction. We have this reaction involving this 3-atomed molecule with this 2-atomed molecule. And that gives us another 2-atom molecule. But note that now we're basically taking one of these 3 atoms and moving it to the other molecule. So now we have sort of a, so here we have essentially something that's like A3 reacting with AB to give us A2 and A2B. So let's also assume that the reaction has an equilibrium constant of 16. I'm just basically picking 16 from thin air. So suppose we mix this sort of reaction mixture. We've got our one of our reactants here, this 3-atomed molecule, and we've got our other reactant there. And note that we don't have any other species in here, so we don't have any of our products at the start initially. So after the system reaches equilibrium, we want to know, what will our system look like? Well, we know that the ratio at equilibrium has to be equal to 16. The ratio between our product concentrations and our reactant concentrations, so products over reactants, has to be equal to 16. Now the products, again, were these two, sort of the A2 and the A2B, and our reactants were the A3 and AB. Now, note that here I've written these as N, capital N, symbolizing a number, because in the last slide, if I go back, we could go through and count up how many of each molecule we have. And so, if we have a small enough number, we can count them and plug in the number that we have. Note that we could use the concentrations, but the size of the box is the same, so we're dividing by the same value for each of these numbers. So I'm going to leave them in terms of number of molecules of each species that we have. So, initial conditions were that we had 9 molecules of the A3 and 12 of our AB molecules. And let's suppose that our reaction occurs 5 times. That means that now we'll have what we started with, 9, minus 5 of the A3 molecules. That means we'll have 4 molecules left. We started out with 12 of this type of molecule. We reacted away 5 of them, and that means that now we have 7 left. We started out with 0 of our 2 products, and that means that we'll end up with 5 molecules of each of our products. So, now we want to know, is the mixture at equilibrium after this 5th reaction? Well, we can plug in our numbers. We know we've got our N values. Let's plug them in. So our products each have 5 molecules, and our reactants have 4 and 7 molecules respectively. Well, that ratio comes out to be 0.9. But remember, we said it needed to be 16. So the mixture is not at equilibrium because the ratio of 0.9 is not the 16 that it needs to be at equilibrium. Because remember, 16 was our the value of our equilibrium constant. So because 0.9 is less than 16, we need to increase the numerator, increase the product concentration, and decrease the denominator, decrease the reactant concentration. So this means the reaction will proceed to the right, towards the products. So the reaction needs to proceed more than 5 times to reach our equilibrium from our initial conditions. And if we had a different set of initial conditions, it may be fewer than 5 times, or maybe more than what we need in this case. So to figure out how many times the reaction has to proceed, let's use algebra and say that the reaction must proceed some X number of times. Note that we could, in this case, go through and just keep guessing, go through and check after a sixth reaction and a seventh reaction and an eighth reaction and so on until we get a ratio there of 16. Now, that's only really realistic for relatively small numbers of reactants and products. But when we get to the real world and we have large numbers of reactants and products, on the order of 10 to the 23, that becomes impractical. So we want to use algebra to do this so we don't have to keep guessing and checking repeatedly to see where we need to go. So now let's write an ICE table. ICE there stands for initial concentrations, a change in concentration, and equilibrium concentrations. So the initial conditions were that we have 9 and 12 of our reactants, 9 and 12 molecules respectively, and we have 0 of our products. Well, we have X numbers of molecules of each of our reactants disappear, and we have X numbers of each of our products form. So that means that at equilibrium, we have what we started with, 9 molecules, minus what reacted, X. So note that we're subtracting here because we had X number of molecules disappear. So we have 9 minus X of our first reactant remaining. We have 12 minus X of our second reactant remaining. And then of our two products, we have X produced at the end. Right? We started with 0. If we started with something other than 0, then we would have whatever that other number is. Let's say we started with 5. It would be 5 plus X molecules of that one. Right? Now we didn't in this case, so we shouldn't write that in this case. But if you start out with some of your products, you're going to have to modify this equilibrium condition over here. So that means that at equilibrium, we then have an equilibrium expression that looks something like this. So remember, we have our equilibrium expression with our numbers equal to 16. And that means that now, if we plug in our values at the end from that right column on the last slide, we have X times X divided by the quantity 9 minus X times the quantity 12 minus X. So now we can go through and solve for X. And again, at this point, because we have relatively small numbers, the easiest way of solving for X is trial and error. So we know that X has to be greater than 5. We can also see that, or we can determine that X must be less than 9, because X equal to 9 makes the denominator 0. So let's go back, right? If we plug in an X of 9 here, then this quantity, that first set of parentheses, will be equal to 0. 0 times anything is 0. That means that now we'll have something, X squared, divided by 0. We can't divide something by 0, so we know that we can't put in a 9 there, which means that we can't go past 9. We can't even have 10. So we have to have some number that's more than 5, that we found out earlier, and it's got to be less than 9. So there are only a few other possibilities, right? We've got 6, 7, and 8. So we only have 3 possibilities that we have to try. In this case, X happens to be equal to 8. So this means that the reaction must occur 8 times for our system to reach equilibrium. And that means that our equilibrium mixture looks like this. So now we have some of our products. We've got one product molecule there. We've got a second product molecule here. Here's one of our reactants. And there's another one of our reactants. So we have both of our reactants around, we have both of our products around, but we have more of our products than we do reactants. So let's now develop this procedure in a more quantitative fashion and with much larger numbers of molecules. Note that you could go back and use algebra to solve as well. So recall that the equilibrium constant expression looks something like this, where we have the equilibrium constant is equal to the concentrations of our products multiplied together times the concentrations of our reactants multiplied together, and each of the products and reactants is raised to a power that is the coefficient in the balanced reaction. So a value of K of our equilibrium constant greater than 1 means that this ratio is greater than 1, and that means that the concentrations of our products are larger than the concentrations of our reactants, and that means that our products are dominating the equilibrium mixture. And this means that the equilibrium lies farther to the right. So we have more of our products around. So in the last example where we had a K of equal to 16, that meant that we have roughly 16 times as many products as we do reactants. You kind of think of it that way. It doesn't totally work out because of the coefficients on each one. But we have more products than we did reactants. And if you looked at the picture, we did in fact have more products than we did reactants. On the other hand, a value of K of our equilibrium constant less than 1 means that this fraction has a value of less than 1. And that means that the concentrations of our products are lower than the concentrations of our reactants. That means we have more reactants than we do products. And that means that the equilibrium mixture is dominated by our reactants. That means that the equilibrium lies farther to the left. So note that the value of K, our equilibrium constant, and the time required to reach equilibrium are not related. Just because an equilibrium constant is, say, above 1, that doesn't mean that the time it would take to reach equilibrium is large. It doesn't mean that the time to reach equilibrium would be small. We're not talking here about the rate of reaction. All we're talking about is at equilibrium. So when things are no longer changing, what would the state be? We may get there really fast, we may get there really, really slowly. So the value of the equilibrium constant and the rate are unrelated. This is because the value of K, uppercase K here, the equilibrium constant, depends upon the change in energy from reactants to products. But the value of lowercase k, the rate constant, depends upon the activation energy. But remember, the activation energy and the delta E, the change in energy from reactants to products, those two energies are independent of one another. You may have reactants and products that are basically at the same energy or just slightly different energy and a very large activation energy. Or you may have reactants and products that are at vastly different energies and a very small activation energy or a very large activation energy. They're independent of one another. So the larger the activation energy is, the lower the value of the rate constant, the slower the reaction will proceed in general. The larger the change in energy, the delta E, the larger the K value will be away from 1, either towards the reactants or towards the products, depending on which direction you're going. If the products are at lower energy, then the products will tend to be favored, and so the equilibrium will tend to be farther to the right. If the reactants are lower in energy than the products are, you have to put in energy overall to get the reaction to go, then in general, the equilibrium will lie farther to the left. So it's often useful to determine the direction that a reaction will proceed, because if we have some mixture, some reaction mixture, and we want to know, well, is the reaction going to proceed farther towards the products or farther towards the reactants? Is the equilibrium going to shift, or is the equilibrium position farther to the left of where we are now or farther to the right of where we are now? That's what we want to know. So to do this, we need to introduce the concept of the reaction quotient, which we symbolize with a capital Q. So the reaction quotient expression looks similar to the equilibrium constant expression, so the one for K, the uppercase K. But the concentrations of the reactants and products are the current concentrations, the concentrations that we have now, not, or at least not necessarily, the equilibrium concentrations. So for K, the concentrations that we have to use there are the equilibrium concentrations, the concentrations at equilibrium. But for Q, the reaction quotient, we have to use the concentrations that we actually have right now, or the moment that we're looking at, to determine which direction the reaction will proceed. So we have essentially two expressions that look almost the same. We're replacing the K with Q, And we're removing the constraint that our concentrations have to be at equilibrium. So that's what this EQ means here. So basically, the top expression here, the expression for the equilibrium constant, is the bottom expression at a specific point when we've reached equilibrium. So if we plug in the equilibrium values for our concentrations of reactants and products, then we get K, which means that basically the value of Q at equilibrium is equal to the value of K, the equilibrium constant. So, for the synthesis of ammonia, we have nitrogen gas reacting with hydrogen gas to give us ammonia. The reaction quotient then looks like this. We've got the concentration of ammonia squared divided by the concentration of nitrogen times the concentration of hydrogen cubed. That's equal to Q, our reaction quotient. So, to determine the direction that the reaction will proceed, we then need to compare the values of Q and K. And we have three possibilities. Either Q is less than K, Q is equal to K, or Q is greater than K. If Q is less than K, then the ratio of our products to reactants is too small, and that means that more products need to be made. If Q is equal to K, then the system is at equilibrium, so no change will occur, no net change will occur. If Q is greater than K, then the ratio of products to reactants is too large, and more reactants will be made. Some of our products will be decomposed back into the reactants. So, let's look at the decomposition of dinitrogen tetroxide to nitrogen dioxide. So the N2O4 gas is reacting to give us two NO2 gas molecules. So the gaseous dinitrogen tetroxide was placed in a flask and allowed to reach equilibrium at a temperature at which Kp is equal to 0.133. So at equilibrium, the pressure of dinitrogen tetroxide was found to be 2.71 atmospheres. And let's say we want to calculate the equilibrium pressure of nitrogen dioxide, the NO2. Well, we know the equilibrium expression looks like this. We have Kp is equal to the partial pressure of nitrogen dioxide squared divided by the partial pressure of the dinitrogen tetroxide, and we know that that value is 0.133. We then can solve for our partial pressure of nitrogen dioxide, the NO2. So we solve that for partial pressure of NO2. That gives us, note here that it's squared, so we then have to take the square root. So we get the partial pressure of NO2 is equal to the square root of our equilibrium constant, Kp, times the partial pressure of the dinitrogen tetroxide. And so we can plug in the values that we have, the 0.133 for the K, and the 2.71 atmospheres for our partial pressure of dinitrogen tetroxide. And that means that once we take the square root, we end up with 0.600 atmospheres for the partial pressure of our NO2. Now you may be wondering here, well, if we look at our units, here we have a unitless quantity, and we're multiplying by atmospheres, and then we take the square root. Shouldn't we end up here with the square root of atmospheres? Yes and no. If this expression is in fact correct, that if this K value is unitless, then we should end up with a unit here of square root of atmospheres. But remember that often we're writing down our equilibrium expressions, or equilibrium constants rather, as unitless, whether or not they really are. That's where this problem is arising from. So this value here, this 0.133 value, is not really unitless. That really has units of atmospheres. So now if we have atmospheres times atmospheres, that gives us atmospheres squared, then we take the square root, and that gives us atmospheres. That's why the units actually really work out. So that was the applications of the equilibrium constant.